All right, hello everyone. Welcome back to another compiler development session, I guess. And uh, last time that we were working on the compiler, I got burnt out a little bit, and I took a 3 days break, I guess. And I spent some time on our project last night, and I implemented the interfaces completely. And I'm going to show you the code. Hi, Hamed, welcome. And I'm going to show you the code for the interfaces and discuss how we implemented them. And then I'm hoping to work on the boolean values. That's my plan for today, at least. So, um, if you recall, based on the specification which you can find here, um, right? So we define interfaces in a manner like this. So we have an ID for the interface, we have the interface keyword, and then all of the methods. And we don't have to mention that a struct is implementing an interface, and the compiler is going to take care of everything that's there, right? So that's what I did. That's exactly what I did. So in this code, I have a printable interface that assumes you have a print function, right? And it's the print function takes no arguments and returns nothing. So it's a unit. And so basically the test struct here, this is automatically a printable because it is implementing the print method. So how does it work? Well, you have a pointer to your struct, or you have your struct directly there, and then you can cast it to the printable, and then you can call the method. And so this time we took a similar approach to that of C++, as opposed to the previous version where we implemented interfaces like Go, right? So basically, the struct has an additional field. I'm going to run the code and show you. Basically, the struct, right? So the test struct has an ID field, which is an i64, and then it has a printable inside, right? So we add for every interface, we add an additional field in here, and when we want to cast it to an interface, we're just going to capture a pointer to that one. And you can never directly instantiate interfaces. You can only have them as pointers, right? Even if in cases like this, so here I is a direct interface, the generated code actually creates a pointer to a printable. You see, so that takes care of a lot of problems that we usually encounter when dealing with interfaces, especially when we have to initialize things on the stack, and it's not going to work out in a good way. So yeah, that's the interface, and it's relatively cheap. We only have a few, you know, GEP elements per each function call and for each casting from a struct to an interface, which is pretty efficient actually. So for example, when I'm casting T to a printable, I'm only calling two GEP elements, and then I guess two stores as well, which is pretty reasonable. And for function calls, the same thing. So we have three GEP when we want to invocate a method, and then two load, I guess, which is very good, if I say so myself. I don't think you can actually go any better than that. Right. So as for my plan for today, I'm going to actually copy this test file Um, I want to start working on Boolean values for today. Right. Just take everything from there. Right. I want to work on Boolean values because we haven't implemented them yet in the current version, but we have them in our specification, and they're really useful to have around. So yeah, that's the plan for today. How's it going with you guys? Is everything all right? Any interesting project over the weekend? Let's see. Right. Um, right. So the first thing that I'm going to do, we need to have two additional keywords. So uh, we have to be able to define something as a boolean and then assign it a true value or a false value. Right. That's the bare minimum of what we need to do. And in the current version, the compiler doesn't understand a boolean or true or false. So we have to start there. And to make things simpler, I'm going to replace these with 0 and 1 for now. So we have to implement one thing at a time, and then we are going to come back and implement true and false as well. Right. So if I run the code on the correct test file, yep, it says that bool is not a type because it doesn't understand boolean. So it assumes that it's a struct, and then it looks at it and it realizes it's not a struct. So it doesn't know how to handle it properly. So what we want to do, we want to first go into our keywords and add a new keyword for that. Right. And then we want to essentially, I'm working on an integrated customer support API. This compiler project is so much good. Thank you, Hamid, but it's not going to be practical for a while. You're aware of the process. It's been 2 years, and every time LLVM updates their code base, you have to start over essentially, unless we reach a state where we can we don't rely on the LLVM that much, which is I'm hoping to achieve in the next 2 or 3 months. Right. And personally, I like to have bool spelled out like this. Hi, Nasrin. This is an English only chat. The live stream on Twitch is English only. Sorry about that. Because there are users who speak English that use our compiler. Right. So personally, I like to spell bool like this instead of boolean the way some languages do, but that's just a personal choice. And yeah, thank you for following. Right. So I'm going to adjust the keyword parser to return a boolean keyword whenever we see a boolean. That's just straightforward. And then I'm going to thank you for following. Welcome to our stream. And we are going to return boolean whenever we want to print the keyword. So now the compiler is going to understand this one, but it is still not going to be able to parse it properly because we have to add it to our primitive type parser. So thank you, Ali Rasuli. Sorry. Thank you, Ali Rasuli, for following. Welcome to our stream. Right. So we also need to update our primitive type parser, and we have created a parsing system inside of C++. that's very interesting usually for people when they see it at first. So the way we do things here, let me show you something better. So for example, for our define parser, which is something that we occasionally use, um, this is how we write the parser. So we start by a base rule, and then we basically apply this operator on our different parsing rules. So here, when we want to define something, I'm saying I expect to see an ID, a column. Thank you, Sepper, for following. Welcome. Right. We say that we expect to see an ID, and then we see a column, and then potentially a type, and then potentially an equal sign and a value. So, and this simplifies writing a compiler by a lot. Previously, we were using Bison and what's it called, Flex. But this approach allows us to uh, you know enable the compiler to have reader macros like Lisp has, which was one of the goals of the language. And yeah, so we wrote this parser in a previous stream, and I'm just going to do the same thing here. I just modify it a little bit by, well, um, what are we doing here? So I want to parse primitive type parsers, and well, I guess I shouldn't have defined it as a keyword then. Um, yeah, it wasn't necessary to define it as a keyword. Sorry about that. So yeah, so all we have to do here is say that, okay, if the type is boolean, return a new type token with t bool, the position, ending position, context, and the source code. Nope, I don't want to become famous. Then okay. So yeah, and I guess I have to backtrack in the keyword parser. We have to move this to the type parser. Right, so where are types defined? Primitive type parser dot header. Is it here? Type enum. Okay. Type enum. So we want to have a t boolean here, and we are able to parse it like this. And if I compile the compiler now, the parser is going to be able to do its job, but the compiler won't be able to generate the code for boolean. So let everything build, and we can go there. Right. So the previous error was bool is not a type, and the next error is going to be cannot cast types. So it doesn't understand what boolean is and doesn't understand how to cast 0 to it. So it's going to complain, or 1, I guess. So we have to work around that, and that's relatively easy to do. We are going to visit our primary type, primitive type here, basically, and say, okay, when you want to generate the type and you encounter a case t boolean, you need to ask LLVM for an integer type with only 1 bit, right? So this would be our boolean type, essentially. And when you want to cast, so I like to treat booleans as integers in my programming, and we are going to tell it here that if you see a boolean, it is a integer, and the size of a boolean is 1, like that. Let's put it down here. And is it signed? No. And right. So how do we cast something to Boolean? We need to go down. The compatible function, I think it is. Right. So when casting things to Boolean, here. So if the key is a Boolean, you want to switch the incoming type. And essentially, if it's a Boolean, we're okay. For anything else, you need to have an explicit cast, right? Because if we go from an integer of size, I don't know, 4 to a Boolean, we are losing some information, and we have to ask the programmer to explicitly cast it by writing something like this, right? And this is what we are telling the compiler. So for Booleans, accept the cast as is. For any other type, ask for an explicit cast from the programmer. And I'm guessing we have to, yeah. So we have to come here and add Boolean to all of the other castings because we can go from Boolean to any other type via an implicit cast. So yeah, because Boolean is smaller than everything else. Right. There we go. Now, I'm guessing this is going to work if I cast it. And if I go to cast generation here, let's increase the size here. Right. So when you're casting, if the target is integer, we can just use the LLVM built-in int cast, and it's going to work out just fine. And it uses the isSign function that we defined earlier, and the other things that we have. So right. So if I compile this as is and run, our program should work. Let's see if it actually does. Okay, so it compiled, and I can run it, and yeah. So the code that we had, this code, is translated into this one. So we create an alloc of size. We create a point in memory that has a type integer of size 1, and then first we assign true to it, and then we assign false to it. So the code generation is working, and we can try that with our if function. So if a print inside if and else printf inside else. Yeah, this is just a very basic test. And if I compile that and run this and then run it, it's going to say inside else because we assigned false to our Boolean at the end, right? Right. So now I want to work on an approach so that we can write a equal true or a equal false instead of writing 1 and then casting it to bool, and writing 0 and casting that to bool. And for that, we need to create a new parser, and I'm going to do it like here, and it's going to be bool value parser. And like all of our other parsers, we have to include this file and create a bool value parser that extends parse rule, right? So, and I don't recall how to write a parsing rule, so I'm going to look at another file. Maybe we can look at I don't know, value parser, right? So yeah, we have to override the scheme function and declare any sub parser that we are going to use. So our scheme function returns a parse result and captures the compile context, the source code, and the position inside the source code. And we also have our constructor. Why aren't you highlighting properly? And I'm guessing we need to have two keyword parser. One for true for parsing the true, and one for parsing false. And pragma, I guess, and we have to include keyword parser as well. So this is basically the signature of our boolean parser. And to generate the code, bool value parser.c++, I am going to right. So I'm going to write the scheme function first, because I think that's easier to handle. Right. So we want to execute parse on TP and FP and return any of it that is true, right? It's just a basic function here, I'm guessing. Yeah. So let's capture the result of true first, and we're going to use the parse method that has the built-in memorization. And this is CC, this is S, and this is position. So if T was true, then return it, and then return fp.parse. So we don't need to check the truth value of fp, because if it's false, our function is going to return false as well. So this works. Next, I'm going to initialize the bool value parser, our constructor basically. And what we want to do, we want to tell TP to look for keyword true and FP to look for keyword false. And we have to define k true and k false. Otherwise, it doesn't know what to do. So k true and k false, like so. And then come here and say if you saw true, return a keyword token, like so, from this position, and the same thing for false. Right. Now down here, we want to return, basically right there, two string functions, like so. Okay. So that was relatively simple. And if I have to register our parser here, so can include a bool value parser. And since it's only two string checks, we can define them here at the end. Register expression rule new bool value parser. Right. So sorry for interruption. Is this source code public? Yes, Hamid. The source code is available at here. We are currently in the C Rumi branch, and the branch you're seeing was updated last night, my local time. You can you can compile it with CMake. It should be straightforward, and you need LLVM 11. There are no readmes or anything in this branch. I'm sorry about that. The specification of the language is also available here if you're interested. And feel free to contribute if you have anything to, if you want to add anything to the language. Thank you for following me, Sam Nova. Welcome to our stream. Right. So I am regenerating the CMake rules and recompiling everything. Oh, K-true was not declared in this scope. That is because we have to include keyword .h. Right. So if I run this now, I guess it parsed, but it's not able to generate the code, so it is producing a segfault. And you can see it actually parsed because uh, you see here it says IDA is true, IDA is false. So there we go. That's always good, I guess. Now we need to convert this to an AST, and I am going to look at my other functions. I guess it's called number parser. Right. So I want to see how number parser is working. Number parser returns a number token. Okay. And I'm guessing we can do something similar. So I am going to define a boolean token here. Bool token, which is a public token. So what do we have in our boolean token? Well, we have a truth value, and we also have a constructor. The constructor should get the compile context, the source code, the starting position, ending position, and the truth value. Yes, right. So yeah, I think we also need to create a describe function, and it should be virtual, and we also need a toAST function. CC, right. That should be correct. So let's start with the constructor, then description, and then toAST. So the token, to initialize itself, we have to initialize the base token, and we also have to capture the truth value. Well, the truth value is captured like that, and everything else we can just store like so. Right. Hamid, if you were able to build a compiler in Windows, I'd be very happy to see that, to see the results. I haven't tested it there. I think someone else was trying to build it on Windows. I don't remember who it was though. I'm trying to look the name up. I think it was Marcel was trying to run it in Windows, but I think he went and used the WSL. Right. So this is our constructor. Oh, full truth. Right. So how do we describe the what we have here? Well, to do that, we can basically look at our truth value and return true or false, right? That should be everything. And for our QAST function, I am going to return 0 for now, and we are going to come back and fix it later. Right. So the scheme is currently returning a keyword token, and we need to work around that and return a boolean token. So I'm going to go here and instead return a parse result with a bt, and bt is a boolean token. And you get your CC and source here. Your starting position is t dot starting position, end position is t dot end position, and your truth value is true. That should be correct. Oh, it should be t dot token and t dot token, right? This is bool token, right? And for the false parser, we are going to capture the results and do the same thing. So instead of t, we're going to look at f, and instead of true, we're going to pass in false. And if none of these were able to match, we are going to return f. So this has an error inside of it, and we are going to reuse the error to complain to whoever called us, right? And yeah, no, don't do anything, right? So that's everything on this end. Now, as for the Boolean token for the 2AST function, I think we can reuse the const integer. Can we not? So const integer. Oh, the problem with const integer is that it always returns an integer, right? And it's always int 64. And we need to create a const boolean then, which is basically the same thing as const integer, but we are going to change the name. And here you have a boolean for truth, and your constructor is going to look like that, and of course the name is different. We do need to implement all of these functions because they are required for the expression function. And so here I'm going to return a new const bool and pass in my truth value included from AST const bool. Right. That should be everything on the parser side, and for the code generation side, we are going to go to source AST and then const bool.cpp, include our header file, and then we are going to take a look at how const integer is implemented. Right. So the way we want to implement this is basically very similar to what we have here. And I'm even going to copy everything and change the names to const bool. Back change, 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 and then change this one as well. Right. So we don't want to do anything in the compiler prepare because it's just a boolean value. How do we generate our expression? Well, we want to return a constant integer of type 1, and the value is either 1 or 0, and it is unsigned. So do that. We have to include these two files. Right. How do we write our constructor? Well, truth is assigned from truth, and we don't need any body. How do we? What's our type? Our type is a. Come on. Our type is type boolean, and we need to include primitive type, and also we need to include we need to include base for the error message. So let's do that. Right. Because you can't assign anything to true. You can't say true equals something, right? Or false. And that should be everything, I believe. Let's regenerate CMake because we added a new file and recompile everything. Class LL context, right. We need to have the LLVM context here as well. That should do it. No declaration matches constant. Oh, right. What about now? Right. So the parser is built completely. The ASD same, and it is now building Room and Rumi, and they are done. So let's see. I can generate the code, and let's write a good test instead of whatever this is. So I want to say A is true, and then say A is false. And this should work, right? This is a very simple code, and it should work, I believe. Compile it and then run it, and it works, right? So the next thing that I want to do, I want to add a not operator. So I want to be able to say not A. And we don't have the required infrastructure to have operands that are, that come before a value. So we have to implement that. And currently, the only operand that we support is binary operations, plus, minus, multiplication, things like that. And we need to add this. So first, let's deal with the parsing problem because the parser isn't going to be able to parse that. You know what? Actually, I'm going to commit everything first and then do that. So commit full values. Right. So we need to first deal with the parsing problem. And the binary operator is a very good example of how we should handle this. So, binary operator parser, I guess. Right. So here we have various symbol parsers and an expression parser. So I'm going to do the same thing. So parser pre-op parser header, and you are going to be run once, and you're going to include an expression parser and a symbol parser. how do you work? Well, you are a public parse rule that has the scheme function, and you have a private symbol parser for exclamation parser, and you have an expression parser, right? And I think let's switch this to C++ mode so we get a color. Right. So the only thing that we need to have a constructor because we need to initialize this one. So let's do that. I'm going to say pre-op parser like so. And I think we don't actually have a symbol for exclamation, so we have to add that as well. So do we? No. So S exclamation like so, and in our symbol parser, let's add it right at the end, I guess. And we need to have a toString function for it. And I think that's everything we need to do for the symbol parsing. Yes. Right. Now, we actually are going to implement our pre-op parser. Pre-op parser.c++ is going to include pre-op parser. And so we need to initialize the parser like so. So exclamation parser is looking for a symbol exe, and that's everything. Add symbol.h. Right. So that's our constructor. And as for the actual parse rule, so we want to ask our exclamation parser to look at that, whatever it might be. And we do that by saying excp.parse ccs position. And if it wasn't there, just return early. You don't want to go into all the troubles. And then I expect you to see a value. So I'm just gonna use our operator to say that I expect to see an expression after that. And now, again, if it wasn't available, just return it. And if it was available, I want you to return a special function, which is going to be a parse results from a new POP token with exclamation point and v as the arguments, and I'm guessing cc the starting position, v dot token dot starting position, and v dot token dot ending position, right? So this should be everything. And instead of v, we should have value, which we get from the token that we get from the second part of this, because the result of this operation is always going to be a tuple token, and we know the second one has our value, so we extract it like that, right? And now to actually create our pre-op token, which is a public token itself, and it has a a symbol. I'm gonna say, you know what? We have a string op and like that, right? So we have that token, and we have a value. We have a constructor that captures the context, the source, the starting position, the ending position, and the OP and the value. And we need to provide a describe function like so. That should be everything. We also need a toAst function, but that is not necessary at this point. Right. So let's start with the constructor as always, because that's the easier thing to handle. Can I copy everything here and paste it here? Right. So how does this work? Well, assign OP to OP, assign value to value, and then do this thing for everything else. That's our constructor, right? That's our constructor, and now we have to write a description method. So I'm going to say that our describe a pre-OP token, you are going to return your OP, and you're asking your value to describe itself after that. And I know that this isn't the best way to do so. Wait, what? Use of undeclared identifier OP. OP is defined here. Pre-OP token. Oh, this should be described. Right. I know this isn't the most efficient way to describe this, but we only use describe in debug mode, so it doesn't really matter. Yeah. Okay, so let's compile that, and I guess I can write a very basic AST for now, something that just works but is not correct, just to test everything. To AST, I am going to say look at your value, whatever it is, and convert that to AST. Right? And this is an AST star. Right. So if I register this in our parser, include a POP parser and add it next to binary operator parser. This is an expression rule, and we want to have a POP parser for it. Registers, capital R. Right. So, so this should work, but it's not going to produce the correct result because you're ignoring the operator completely and returning the underlying value, right? So, but this is just for the testing the parser, so it's okay. Right. Come on. Okay. So you can see that it does compile and it does run, but it says inside else, where it clearly should say it's not A, which is false, so it should say inside if. So we have to create an AST here. to handle that properly. Right. And to do so, we are going to create another class called a pre-OP in our AST module. So pre-OP, well, yeah, pre-OP.header. And it is going to, you know what? I'm going to include this one. And I'm going to just change binary OP with pre-OP. And we have only one value. And we don't care about that one, and this should be value, and this should be pre-OP, right? Yeah, I think that's correct. Right. And to generate the code here, I am going to say, okay, return a new pre-OP with your operation and whatever this is. Okay. Also include it from AST pre-OP, like so. How long have we been streaming? 54 minutes. Okay. Surprisingly good progress so far. Right. That's everything on the parser side. And for the AST, the op.c++, we are going to be lazy and do that. Change that to p-op, and then replace this, replace that, this one, replace that one, replace that one, replace that one, replace that one. Right. So the constructor doesn't have LHS anymore, so we can get rid of that. And there is no RHS, it's value now. Right. No LHS, OP is from there, and value is from there. When you want to compile, compile your value. There's no RHS, and then this is the hard part. Ask the type of your value if it has pre-OP that. And doesn't support operation. Okay. So we have to add has pre-OP to all of our types, but we can do that. We also, well, the prepare function is easy. The type should be like that, and the expression generation should be like that. And the alloca generation, well, technically it shouldn't return an error, but for now, we're going to do that. There could be some pre-operations that have an alloca, right? Yeah. So I'm not gonna complain just out of the box. Right. So we have to add a pre-OP gen and a pre-OP type resolve, and it has pre-OP to all of our types, which is going to be fun. So virtual. Thank you, Safari, for following us. Welcome to our stream. How's it going? Right. So that's our as pre-OP, and it is 0 by default because every type has to implement that for itself. And then we have the type resolve, POP type resolve, which is 0 again. And then we have to have a void star for POP gen, the expression star value. Something is missing. Oh, the compile context. Right. So technically the pre-op is done at this point. We just have to implement these three methods for all of our types. And to make it easier, I'm going to regenerate CMake for myself, and I am going to just start copy pasting. Right. So the first type, the primitive type. Copy these to here. Let's enable golden ratio, and let's toggle by the screen. Right. So I'm going to paste them here. Remove the equal 0 part and do it like that, and say we are overriding. Right. So primitive type, and then we have oh, come on. Right. We have pointer type. We have function type. We have, what else do we have? Primitive, function, pointer. We have named type, I believe. We have a struct, public. Right. And I think we also have interface. Yes. So that's all of our types. Wow, that's a lot. So yeah, so let's implement them one by one, starting from interface. So the interface doesn't really have a pre-op, so I'm just gonna do it like this. So if you ask me if I have an come on, autocomplete. If you ask me if I have a pre-op, I'm gonna say no. If you ask me how to handle type of a pre-op, the OP type resolve, I'm gonna say I don't know. And if you ask me how to generate code for a pre-op, I'm gonna say I don't know. Right? And this is going to be everything for our interface. I'm going to copy this one, kill that file, repeat that for struct. Right? Yes. Kill that file, Name type is a little bit tricky, so let's ignore that for now. Function type. Right. Function type .c++. The same thing. Function type. Function type, and then function type. Did I change it for struct as well, or did I forgot to do that? I forgot to do that. Struct type, and a struct type. Right. So that's a struct type. That's function type. Let's copy this one for the next type, which is I guess we are done. So name type. Name type is a special because it doesn't do anything on its own. It's just a proxy for another type. So we're just going to pass everything to our underlying type, right? So we're just going to say, okay, I don't know. Do you have this OP? I don't know. Ask my resolve type. Ask my resolve type for has pre-OP with CC and OP. Do you know how to resolve this one? I don't know. Ask my resolved type if it can resolve this for you. Pre-op type resolve, CC, and then O. Do you know how to generate the code? Ask my resolve type how to do it for you. Pre-op type resolve, CC, and then OP. Oh, type gen, it should be not resolved. Type gen, and then we need to also pass in the value. POP gen. Right. So yeah, so this is for name type, and now the real trouble, which is primitive type. This is going to be a hard one. Let me copy the function definitions so I can reuse them. Right. So you have a primitive type here. Rename that. Rename that. Okay. So do you have a certain OP or not? The only OP we have currently is not, and we only have it if our key is boolean. So there you go. That's our has pre-OP. Do you know the type? So if your OP is, I guess return false for everything else. Do you know the type? Well, if your key is T boolean, your type is going to be this. Otherwise, you're not going to have a type. Do you know how to generate the code? I certainly do. If you're dealing with a not and if so, if you're dealing with a not and if your key is boolean, we know how to help you. Otherwise, we return 0. So how are we going to help this? I am going to look at if for to get an idea of how we handle it there. I think we have to create something called a I compare and no. I actually don't know what the name of the operation is, so I'm going to write a basic C file. We don't have boolean in C. We have a, which is going to be not 0, and then return 0. So let's see how does that compile. it is casting that statically. I don't like that. Test.c. Right. Let's say you are 0 and then a would be not a. That should tell me, because I'm passing an optimization of 0, it should tell me what the operation is. It is XORing it with a true. Wait, what? So you're comparing it with. So you seriously don't have a not operation? Is that what you're telling me? I don't believe this. I think we actually do, and the reason why it is doing this to me is because I am using int here. But I think C doesn't have a Boolean type, so yeah, it doesn't have a Boolean type. Shoot. You know what? Let's look at the LLVM documentation. So LLVM IR, the language reference, and we should have a not operations here. Not. No, 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 no. Thank you for following me. Is that Shahriar? I'm guessing. Welcome to our stream. Okay, so this is going to take a while. If I Oh wow! Welcome, Titled. Hello everyone. Welcome to our report. Welcome to our stream. Wow. Welcome. How's everyone doing? Going up to the family. Okay. Cheers. Thank you. Thank you for the rate. Hello, Temperous. Welcome to our stream. Okay, I'm going to close that for a second. Welcome everyone. Thank you for joining our stream. We are working on the Rumi programming language. Oh, thank you. Then I don't know how to read that. Welcome, welcome everyone. Right. I'm guessing. I'm guessing I have to do something like this. C++ in Vim. Nice. This is Emacs. But yeah. Oh, there was a create node. So yeah. I'm just going to write that, and I'm going to describe to you all what we're doing, and then we can keep going. Right. Let's hit compile. So we are working on the Rumi programming language, and it's a language I've been working on for 2 years now, I believe. And we are rewriting the compiler to allow us to have macros and something, some nicer features in the compiler. And the documentation for language is available here. I encourage you all to read that, and the implementation is there as well. And we are working on booleans at this point. That's actually fine. It reminds me of something. If you Google V, Google is gonna say, yeah. Oh, it doesn't work for Vim. It works for V, right? German Emacs. And if yeah, I mean that's just an inside joke, I guess. We have a problem because pointer type doesn't have. Okay, we forgot to implement these three functions for pointer type, which we are going to do now. What were they called? Let's look at function type and copy the code there. So pre-operations, pointers don't have any pre-operation at this point, so we are safe to return false when the program asks if it has a pre-operation. We are safe to return 0 when they ask for a type, and safe to return 0 when they ask to generate the code for a pre-operation, right? And we are doing all of this to enable this little thing here. Okay, it compiled. And does it actually compile our test file? It does. And you can see, yeah, it is doing the same thing C did. So it is XORing it with true and then negating it, which is okay, I guess. And if I run this one, it says inside it. So none is working correctly, and I'm happy about it. Okay. Right. So what else should we do? We can implement the equal operation, the greater, less than, all those things. Or I can show you a tour of the language if you guys are interested in seeing what we're working with. Let's do that. It's been a while since I've done that. So I'm going to open the old code for Rumi available here, I guess, and open up the test one. Right. So this is the Rumi programming language, and it's a compiled, statically typed language. And yeah, so it has some very specific features that I really like. Specifically, we have the compile directive. And if you add at compile before any function, it is going to be run inside when you're compiling it, right? So you can write, for example, test in this way. So here I'm testing to see if the rem function is operating correctly, and if it is not, I'm printing the error and complaining. And you can do some other interesting thing as well. So for example, you can define a function inside another function. Yeah. So here we are inside a functional test function, and you can see I'm defining one, two, three, four different functions inside of that. And the other thing that we have, the compile directives are really powerful, and they allow you to modify the source code in compile time. For example, this struct doesn't have an ID field, right? But I'm calling an add ID on it, in which we add a field to our struct. And then you can see in the code, I can actually say m.id equal to and print the value. These all work. So yeah, and we are rewriting this compiler because the first version didn't have a proper structure for types, and we encountered a lot of problems when dealing with casting and when dealing with weird stuff that you want to do with your compiler. The second rewrite was done inside of Rumi. If you actually look at the code, I guess it's well, should be this one. Yeah. So the second time we rewrote the compiler inside Rumi itself, and it was working flawlessly. But then LLVM updated itself to version 11, and it broke a lot of things, and it wasn't really worth it to go back and fix everything. So I decided to rewrite the compiler and forget the dream of having a bootstrapped compiler, and that's where we are. Right. Anything you guys want to see, or should I continue doing what I was about to do? Feel free to interrupt me if you have anything to ask or you want to see. Right. So I want to be able to. Oh, thank you for following Tattoo Forever. So I want to be able to say things like I is an integer. Well, I is like this, and check to see if I equals 3. And at this point, we can't really say that. The compiler doesn't really support this one because this operator is not defined. But we can easily define it, and I am going to do that. So if we run this at this point, it's going to complain that I can't parse the file at that index, right? And the index is here, basically. So you know what? I think I didn't commit my progress, did I? add everything, commit, boolean, pop. Right. Let's go back to here, I guess. Right. So how should we handle this? Well, I think the best place to handle it would be in our current binary operation parser. So we have this parser. Um, right. The parser, please. Yeah. We have this parser that you know does various things at this point, and what we are really interested in is this one. So to actually parse different things, we try all of our symbols. We try the add symbol, we try the minus symbol, the multiplication, the division, the remainder. And we are going to add another one here. So is our OP equal to equal? And I am going to say uh, equal parser. And then if it was, return it. Now we have to define the equal parser, which we do in a similar fashion to other things. So we say equal parser is looking for a symbol EQ. And the compiler doesn't know what EQ is, and it doesn't know what EQP is. So one by one, where is it? Right. So we are going to say you have an EQP parser, and in our symbol parser, we are going to say you have EQ as one of your symbols. And how do you parse it? You might ask. Well, if you see an equal, look at the next thing. And if the next operation was, if the next symbol was also an equal sign, then you have a EQ symbol. Your position should be increased by 1 and you should break. Otherwise, you have a regular assignment, right? So that's the parsing of equal. I'm going to comment it for myself here. And how do you print it if you want to debug something? Well, case EQ, return EQ, like that. And this should work at this point. I think, at least. Let's see if we encounter any problems. Thank you for following Neonoc. Welcome to our stream. Right. Compile that, and it's still saying that I cannot parse the file at that index. Let's see. Let's look at our code. Right. So why can you not parse it? Did you reach here? Oh, right. Because, yeah, it should be like that. So we see our first value, and we see equal, and then we should see another value, right? Yeah. You should be able to parse it now. Compile, and right. The parser should work, but the code generation should produce an error. Yeah. Unknown OP in PREC. Right. But the parser did work. And now we are going to go and handle that. So here, what is the we want to handle EQ at the last possible step. So first deal with multiplication, division, and remainder. Then try to deal with plus and minus, and then finally look at the EQ. And that should be it. How are we using this function? Just out of curiosity. Right, yeah, that is going to work. Compile and run. Right. So the parser is not complaining anymore, but the code generation is complaining. It says, I don't know how to support this operation. And you can see that the parser is parsing that correctly. It says we are expecting ID I to be equal to value 3, right? So how do we generate the type? Well, to do so, we are going to look at primitive type, and when we want to deal with uh, operations, I guess has OP is the name, right? So if the operation is equal, you always have the OP for our primitive types, right? All of our primitive types support this operation, except maybe the integer, maybe the string at this point, but we don't. I guess I can explicitly say that here. So and key is not equal to type string. So if you have equal and you're not a string, I can do that for you, right? And what would be our type? Type result. OP type. Come on. OP type result right here. So if you encounter an equal, your type is always going to be a boolean, right? So I'm going to say return new primitive type with type boolean, like so. Return new, right? So that's how you resolve the type. And how do you generate the code? OP-gen. Well, so here we are going to say if the OP is equal. So I think LLVM has an equal thing directly. Create compare. Right. So we have a create compare, but I'm not sure which one we should really use. Uh, you know what? Let's actually look at the documentation for create compare and see if it is. Come on. LLVM create CMP. Let's see if we need to do specific things. Right. Definition at line whatever. Let's go there. Create compare. Okay, so it handles floating points and integers, so we don't really need to do anything. And we can just say create compare left hand side, which is an LLVM value star left hand side expr_gen, and right hand side, which is expr_gen cc, like so, and just return that. You don't need to do anything special. Expected at least 3, have 2. What else do you expect? So you want to see predicates, value. Oh, what is that? What is this one? Let's look at that. I'm not sure. I've never used this directly. Oh, so we have. Wait, what? Can you look at the previous code? So you are passing predicate to create fp compare, and I guess I've used that in the if parser. CMP, yeah. No, I haven't used it here. I'm using not equal. Thank you for following, Sina. Welcome to our stream. Right, so I'm not sure what the predicate should be. Let's look at the possible values. So we can have. Oh, I have to explicitly say what I am. Well, I expect to see an equal. Do you have that? Do you have a create CMP equal? No? I know you have not equal. Oh, you have EQ. Create. Right. And I guess EQ is different for integer and floating points. Yeah. Right. So this is what we're going to do. We are going to close that, and we are going to say, where was it? So if we are dealing with an integer, we want to say return cc llc fielder create integer compare eq, and this will be return, of course. Stop complaining. And yeah, so what is your argument? Well, it is this one. Otherwise, I am assuming it's a float, like that. So no member create ICMP are you sure? ICMP Q is uppercase. Okay. We have that. Create FCMP. Okay, what is we have O and U. What does that stand for? Let's look at the file. So we have a create FCMP O, which is referencing OEQ, which is OEQ, this one. If ordered and equal, and then we have a UEQ if unordered or equal. I don't know. So I'm not going to write the code for floating points at this point. I'm going to throw an error. Says not supported for floating points, and we can deal with that later, right? Not supported. Well, let's say this is not supported for floating points, right? And this would work for integers. And I want to see it in action. Oh, no declaration, primitive type. What are you complaining about? Pre-OP type result, right? Echo. Okay, and this should work technically. Let's see it in action though. Right. Compile, and then compile, and then run inside if, because the code that we were running was asking if integer is equal to 3. So can I do I minus 1 is equal to 2? That, in theory, that should also work, but let's try it out. Actually, let's look at the code. So we are loading our alloca. We are creating the alloca, storing 3 inside of it. We are loading the value, subbing 1 from it, and then comparing it to 2. That should work. But let's just see. Yeah, it does work. So there we go. We have EQ for integers. And then the other important things is, these operations. We have to implement all of those for integers at this point. You know what? Let's actually be smart about something and has OP. So I want to say is int key, for now. And I guess we have to look at the target type as well, right? We can't just compare integers with structs or functions. So it only makes sense if we do this. And we're going to say if what is it called? XPcast, if compatible, right? So if it's compatible, if the target type is compatible, look at our signature and they should both be integer. If it's not compatible, then complain about it. Is that okay? No. If the compatibility is not equal to incompatible. Is that okay? I think so, it should be. Let's compile. Yeah, sure, save. You're compiling and run this. Do that. Yeah. That's okay. I'm going to close that one so that it doesn't flicker on me. Right. What should we do next? Let's start with something easy. So I'm going to say, is it greater than 1? And we have to define the greater than operator. I guess we can define all of them at once, right? Let's do that. So we have greater than, we have greater than equal, we have less than, and we have less than or equal. So those are our symbols, and like so we can define them in our symbol parser. Do we have anything to build up of? No, we do not. So let's add something here. So case this one, and I'm going to copy this entire thing, and it is right. So if you see a greater than and an equal sign after that, it should be GTE. greater than or equal. If you only see the greater than, it should be GT. So that's our first symbol. And the same thing for less than, only in reverse order. So change it like that. This should be L and this should be L. So that's the parser. And as for the describe method, we can run so GT return greater like that. GTE return it like that. And then less than and less than equal, return it like that. So that's the symbol parser. That way we have all of the different symbols. So we can parse them. Now we have to tell our binary operator to look out for these types. Oh God, that is going to be a lot of things to do. But I guess binary operator dot binary operator parser dot header, right? So we have symbol parser, GT parser, and GTE parser, and we have that and that. And you know what? I am going to move this one to a new line as well. Should we add a not equal parser here as well? Or should we do that later? So let's do it, now that we are doing everything. Not EQ parser, right. And you need to have a symbol for not EQ, like so, and in our symbol parser, case not EQ, return that. And here, when you see that, I'm going to ask you to look at the next character. I know I have the code somewhere here. I'm going to ask you to look at the next character, and if it was unequal, we are dealing with a not equal, so change it to an EQ, like so. So that's the symbol parser. That's the binary parser. And we have to come to the binary parser.cpp, initialize all of these 5 new parsers with their symbols. So NEQ parser would be symbol NEQP. And I'm going to be smart about this. Copy this one, paste them here, delete that, remove that, remove that, new line. Right, so create a macro that jumps to the beginning of the next word, add a comma, jumps to the end at S underline, goes back, yanks the word, goes to the closing parentheses, back, paste, and then deletes, and then comes down like that. Now do that. Okay. So that's our binary operator. I know that was a lot more work, but that was, I really enjoy writing macros like that in the editor. Okay. Next, we have to mention the operator precedence, which they are all here. So I'm going to say NEQ, GT, GTE, LT, and LTE. And that should be case, right? So that's the precedence. And I think that's everything in the parser, at least. Yeah, should be. So let's write the code. Let's write the test code. Um, I'm going to say, okay, if I, which is 3, is less than 4, and then printf correct, else, you know what? We don't even need that. Printf wrong. So that should be that. If I is less than equal to 3, that should work. If I is greater or equal to 3, and if I is greater than 2. And if, you know what? If I is not equal to 2. So that's our test cases. If I compile this at this point, the parser is going to be able to parse that program, but the code generation doesn't know how to generate the code, right? Yeah. Okay. So let's run that. Yeah. Oh, can parse file at index whatever. Why not? Oh, we forgot to actually use our parsers here. Right. Can we be smart about this too? I'm guessing we can. Right. So, what do I expect to do? Starting here, jump to the comma, delete that. Um Delete that as well. Capture the next word. Go up, write temp equals v1, whatever. Paste, add a semicolon. If temp, return temp, like that, vp. Then come down, delete that, add a new line, go to the beginning of the first line and stop. Now do that again, 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 and again. Now all we have to do is add the comments, and that should be it. So this is equal, this is not equal, this is greater than, this is greater than equal, and this is less than or equal, and this is less than. Oh, here. Okay, right, that should work. Yes. Okay, it compiled. Can you parse it? Yes. It parsed it and it says, I don't know how to implement this operation for primitive type, which is fine. I am going to thank you for following us up. I hope I spelled that correctly. I pronounced that correctly. Welcome to our stream. Right. So let's come here. So we have to tell our program that you can do the same thing for. Well, I guess you can do. I guess you can do the not equal for possibly all of the types, and for greater or greater than or equal, or less than or less than or equal, we can only do those on integers, right? Oh boy, this is the wrong place to do that. Oh no, I thought we were in the has op. I thought we were here, right? So yeah, also not equal should be like so. Op it could be not equal, right? And if they are not incompatible, right? So we can do not equal on anything that we can do equal on, and we can do all of these operations only on integers and only with compatible types. Is that correct? I think so. That looks correct to me. Yes. Okay. Now, this isn't going to complain, but the operation generation is going to complain. We have to define it for multiple operations, and I am going to copy this line here. Maybe we can be a smarty about this too. Like so. And I guess also OP not equal. Right. So what do we want to do? Let's say we start at the beginning of the line, record the macro, jump here, say if, remove the closing parenthesis, go to the end, close it, open a bracket, look to see if you're dealing with an integer, and then return cc llc builder create create ic something. I'm not gonna complete that, and then do it like this. I'm not gonna generate the LHS and RHS in the beginning and then call them for all of the types, because there are cases where we don't want them generated, and it's going to cause some errors if we do that. In case you are wondering why I am repeating a lot of code. Right. And then come down, go to the beginning of the line and stop the macro. Run a macro on this one. Come on. Did you not hear me? Oh. Run the macro on this one. Takes a while, but it does the job. And then run the macro on the next two lines. Right. And now all we have to do is go and complete those, which we can do easily once the macro finishes executing. Yes. Okay. So, how do we want to handle greater than? Well, you have compare. Oh, we have signed and unsigned. Oh, I wish I knew that beforehand. Right. So if is signed, I want you to compare integer compare. This is greater, signed greater than, and then whatever might come afterwards. Else, uh, unsigned. Let's copy that and paste it here. So this is greater than or equal, so it should be GT sign greater or equal, right? GE. This is less than, so I'm going to copy that again. Oh, forgot this one. So less than, I'm going to copy this again. If I knew this beforehand, I would have incorporated that into our macro. So yeah, so greater than becomes less than here and less than here. And the same thing for less than equal. So this should be equal, and this should be equal as well. For the not, I know that it's ICMP not equal. Thank you for following me, Hassam. Welcome to our stream. Welcome. Right. If I compile this, is it going to work? Oh, I forgot to do the type resolve. I'm not going to run this because I know OP type resolve. OP type resolve, right. So if it is not equal, or it is less than, or it is less than or equal, or it is greater than, or it is greater than or equal, the answer is always a boolean. Right. Compile that, and we should be able to run it. Right. Okay. Run. Segmentation fault. Okay. Where are we getting the segmentation faults? Well, grind. Oh, it. That is really weird. So we got a segmentation fault the first time, but we didn't get one when we ran it with Valgrind. That is really problematic. Can I run it with GCC or no GDB? I don't recall how to actually use this. So I have to say load. No, I have to say GDB bin rom, and then run it with with test 5 -b. So the lookup is failing for some reason. Yes, the lookup is failing. That's something that we have is potentially completely unrelated to what we're doing here. But let's see. Oh, right. My function names are wrong. Okay, so but that's not good. The compiler should complain instead of throwing a segfault. So let's actually look at that. In the fcall cpp line 26. So here, right, in short function we have a to do there. So I'm gonna do that real quick. So if there is no result for a lookup, say debug none, didn't find function ID, and then exit. Okay, that should potentially work. Let's move that to do. Okay. Run this. Another segment fault. That is very interesting. Oh, it is because I don't. No. So what? Why the next segment fault? Ah, come on. Run it with test 5. Oh boy. Tag type legalizer. That means that our program is correct, but not really. So there's a type mismatch somewhere. Uh, I'm guessing it is because of the if operators. Um, it might be because of this. So we are comparing a boolean value with a zero. So in the if statement, it's all in the if statement. I know I'm casting it to some other thing. Right, I'm comparing it with a zero. So we shouldn't do it like this. The way we should handle it is by look at the value, which is where is the value in the condition, and look for the type. And look for the type. Thank you for following me, Ignited Moose. Welcome to our stream. So I'm going to add a dynamic cast for primitive type, and condition like that, right? So if you can cast to a primitive type, uh, include that. If you can cast a primitive type and your key is a boolean, I guess I have to do a base resolve as well in case we are dealing with a name type. But, that's not going to work. God damn it. Right. So if you're, that was correct. So you have to deal with the base type. And here, if your key is boolean, you want to do something interesting. Bool generated v is false by default, and here we're going to say, okay, we have generated v. All you need to do is to we yeah we don't you don't need to do anything basically because v is generated up there, and that's enough. The type is correct, right? So if not generated, generated v. Okay, I think I spelled that wrong, but I'm not gonna stress on it now. So yeah, if it isn't is condition a boolean, basically that's what you're asking. So if it's a boolean, we don't need to do anything else. If it's not a boolean, we have to compare it with the correct type. And I guess we should handle this elsewhere in the compile function. Thank you for following me, Ali Reza. Welcome to our stream. We should handle this in compile, not here, but this is just to get it working. And if it did work, I am going to handle it in the proper section up above. Right. I think we should call a cast to boolean and expect it to work. Right. So run that for me. Exactly, it worked. So that was the problem. But let's see if I done everything else correctly, and then we are going to go and look at the casting. Yeah, everything is correct. Right. So basically, we shouldn't check v. We shouldn't do any of this. We should just have a condition vr. And this is potentially solved if we look at the boolean type. So if I go to compile, check condition type. So if condition dot type resolve, I guess it's type resolve, isn't it? Type, okay. If it's look at the compatibility with a boolean type, I'm going to add that. And if it was anything other than okay, we want to do something. What do we want to do? Well, we want to say our condition should be a cast expression, a new cast expression. What's the constructor in a cast expression? I don't recall. I think it is. Oh no. Nope. It's cast. Right. And it is an expression which is the previous condition and a type which is the boolean type. And that should handle things for us. We have to include cast.h, and to introduce the boolean type, I am going to say boolean type is a new primitive type that has t boolean inside of it, and this is also right. That should potentially solve our problem. So we don't need to cast it manually down here, but I'm guessing there's a potential error when we are downcasting from integers to boolean, and we can solve that by going to primitive type. And then cast generation. So we have to do a special operation when we want to cast things to boolean, right? Because it's not enough to truncate the integer. For example, if you truncate this, the truth value of this is true. But if you truncate it, it's going to look like this, and the compiler is going to treat it as false. So to work around that, I am going to come here and we are going to look at the target type, which is in PT. And if PT key is Boolean, we want to take a special precaution. So what do we want to do here when the target is Boolean? Well, we want to create a 0 element, and we want to do that. And we want to do a return here. Right. So a 0 not of type 64, but of whatever type I am. So whatever type I am, this is LLVM type whatever type we are, get a 0, and then compare my actual expression with that. Okay? So that's basically the downcasting that we want to do. Right. And I can get rid of this. I can get rid of this. And yeah. So we should do the same thing for while, but let's see if it works for if. And then we can look at while. Okay. Let's actually write an if statement that uses numbers. If one printf sanity check for boolean integers. New line, else, semicolon, else printf wrong. Okay. And let's do it on something that is more complex, like that. Not complex, a bigger number. Right. So compile and create the executable and then run it. Run. Okay. So it didn't work. It didn't work. Why did it not work though? Um, it didn't work potentially because either the cast is wrong. You know what? Let's actually find the location, and then we can judge it there. I'm guessing this is it. No, this is less than, so it should be. It should be. This is less than equal. I don't know what that is. Greater than, not equal, and then it should be. Is the last one not equal? So we don't have that at all. Are we even generating the cast? So not equal jumps to if f18, which jumps to if continue 17, which just jumps to false. Interesting. So the compiler has looked at this and decided, okay, this is false. Let's just get over it with it. I don't like that because this isn't false. This is actually correct, right? So what are we doing? Let's look at the if code. So we are creating a condition BR based on the truth value of v, which is only an expression generation. So this is only relying on this one. Oh, I know why. I know why. So when we are casting, casts or compatible, I guess. When we are casting here, we have said that it is. So whenever we are casting the boolean, no, that's fine. Only boolean is okay. Everything else should be cast explicitly. Okay. So this is fine, potentially. Okay, I'm going to take a short break and I'll be back in less than a minute. Please don't go anywhere. Yeah, we can continue after that. I just need to take a short break. Okay, I'm back. Thank you, OG with Uzi, for following me. Welcome to our stream. Okay, so we were dealing with the casting problem that we encountered, and we can potentially fix that. Well, we have to find out what the real problem is, though. But I'm guessing that the problem. Oh, it should be here. Okay, where's my keyboard? Come on. Right. So I'm suspecting that this is the real problem, right? Oh, so yeah, so this isn't being invoked because we are saying if the target key is boolean, we should look at our own key, not the target key. Okay, that solves that. If our own key is boolean, do this. The target key is something else. And then I guess the next problem would be the type gen. So the type gen should look at the target key like so, and that should solve the problem for us because, as I said, it was truncating the integer, so 1000 or whatever it was would only be zero in the end. Right. So compile that, create the executable, and then run it. Sanity check for Boolean integers. Right. So that solves the problem for if, and now we have to do the same thing for while. So how did we handle that? So we look at the compile. If I recall correctly, yes. We can remove the to do. I'm going to just write that directly there. And include primitive and cast. Primitive and cast should be included here as well. Right. So convert it to a boolean if it's not already a boolean, and then when generating, You generate your condition. You don't need the zero const, and you don't need the comparison. You can just use that as is for your conditional jump. Let's compile and try that. So I'm going to say while I printf I times I is, you know what? Let's do it like this. And we can pass in I, and I times I, and then decrease it by 1. And that should potentially work. Right. So compile that, then run it. Yes. So 3, 2, 1. So the condition works here because I is an integer and is working that. So I am going to commit this one. So what did we change? We added integer comparison. Also fixed if and while casting. Right. Push it to the upstream. Done. Okay. So now we wrote a FizzBuzz program. Do I have it? Example. What was it called? Example FizzBuzz, right? We wrote a FizzBuzz program very early on, and we didn't have a lot of the things that we have now. And now we can visit that again and rewrite the program. So we have a target. You're looping on that. If I what? Yeah. So if I modulo 3 is equal to 0, print fizz. If I modulo 5 is equal to 0, print buzz. And if I modulo 3 times I modulo 5. So let's add parentheses to this mess. So if this is not equal to 0, or wait, I can add them in the number. And this is a very basic FizzBuzz. Permission denied. Oh, bin room example FizzBuzz. GCC that and then run it. Yes. So, oh, this should be if this multiplied by 0 is not 0. Okay, that should be it. Right. Right. So we get 1, 2 fizz, 4 buzz, fizz, 7, 8 fizz buzz, 11 fizz, 13, 14 fizz buzz, 16, 17 fizz, 19 buzz. So the fizz buzz example is updated, and as you can see, it is much more readable than the mess that it was before. We actually have comparison, and the integers are handled correctly by the compiler, so we don't need to worry about it. The next thing that I really want to handle is the AND operation and the OR operation because they're really useful. I just don't know. I just don't know where to begin. So let's write another test and say if let's reintroduce I as 15. I want to say exactly what I want to do there. So if I modulo 5 is 0, and then I modulo 3 is 0. Is that what I want to say? No, I want to say this one, sorry. Mm, right. So if either it is not divisible by 5, come on. If it is not divisible by 5, or it is not divisible by 3, I want you to do something. And, sorry, not or, and. Right. And so here, the printf should say wrong, because we are divisible by 5, so this would be 0, so this would be false, and then the whole thing should be false. And here, we would say printf right, or correct. Okay, and the thing that we have to keep in mind is that so if we are dealing with an and the first part is wrong, we don't really want to check the second one, right? And the reason for that is, when we are dealing with pointers, assume that p is a pointer. We might say p and p dot id is greater than 5. And if we don't do that and check for p and say, okay, this is false, let's see what the other thing is, and we go there, we are going to get a runtime error because p is null and null.id is not defined, right? So we have to keep that in mind. Okay, so let's start with the symbols. We have and, or. Don't tell me that I already have this. Okay, I'm going to say and I'm going to say pipe. I don't know why, but So in the symbol parser, I guess I already have the and, so let's start there. If the next position you also see and we are dealing with and I want you to tell me that. Okay? Now, if you're dealing with not and the next position, not, you're dealing with this one, and the next position is the same thing, the pipe, we're going to say is p equals s pipe and break. Also increase the position. So what happens otherwise? If we go to the default branch, it is going to, we have to return 0. Okay, so I have to return 0 at this point. So if I see a single pipe, that's an error. All right, because we don't have single pipes defined yet. We might define them in the future, but not now. Okay, so that's the symbol. That's a symbol parser, and we have to define and we have to define the what was it called? Pipe. Okay. Okay. Do we need anything else here? I don't think so. Okay, now we can go to our binary operator. I'm guessing it is in here. We want to define two new symbol parsers. The first one is and parser and or parser, right? Then we want to initialize them. So the and parser is s and end, and the or parser is s or sorry pipe. Is that correct? Yes. Thank you for following me, Black John Rose. Sorry. Thank you for following me, Black John Rose. Welcome to our stream. Okay, so I want to check and first. So if you can see a value followed by a and parser. Oh, what the hell was that? Right. Return it, and if you see a or parser after that, also return it. Okay, so that's everything here. We have to handle the precedence, and for that, I am going to increase this to 2, that to 1, because and or should be dealt with at the last possible step. So s and or s pipe have the least important precedence. Um, pipe, that's correct. Okay, I made a mistake here. It should be pipe, and potentially I've made a mistake everywhere else as well. So pipe, yes, in the symbol parser as well. Pipe, and here as well. Pipe. Okay, so we do that, and that is everything for the parser side. If I compile that, the compiler is going to parse my program, but it's going to complain that I don't know how to generate the code for it. Right? What's that? Okay, I can ignore that. Okay. So let's do that. Oh, it actually... What? How? Oh, because I'm running the I'm running the wrong code. Okay. I want to run it on test 5. Yes. So it can parse it, but it doesn't know how to generate the code, and therefore this segment it is throwing an error. Can I handle the error somehow? In the if compile, I don't want to. Line 27 of if. Right. So potentially in the binary operator, when we ask for compile, you should tell me if the OP doesn't have that thing, right? And I have called compile on you, but you are not telling me that. So what's wrong? Um, condition.compile. So this, wait, line 27. So it, ah, so if uh, wait, what? Left hand side type cc has OP. Right. So this should be invocated. Why isn't? Why is it not? Uh, aren't we dealing with a binary operation here? I think we are. Yeah, I just wrote the code. We are. So here, the compile function to call this one, and then we compile the left hand side. We compile the right hand side. We look at the type of the left hand side and ask if it has the operation. So I am going to say I am called just to see maybe there's something wrong somewhere else. We shouldn't get a seg fault for things that we have handled, right? I'm called. Okay. Are you called? You know what? Let's also print your OP so I can see what you're called with or for. Because we are dealing with a lot of different things there. Okay, run that. Right, so it is called for and, and it is... Seriously? Primitive type, come on. Primitive type, C++. Has OP, right. So we return true here, or if you're one of those operations, you're not one of those operations, you're not one of those operations, and then we return false. So what's your fucking problem? Left hand side dot type as OP. So the left hand side type is primitive, isn't it? You know what? Let's yank this one, paste it here, do that. Maybe I have no idea what's happening here. Yeah, so one for everything and one for and. That's weird. So let's look at this one. So you won't be able to pass through this one. The closing curly bracket is there. Oh, it is captured here. Right. It was captured here because of the string. It should have been an and, not an or. Yeah, type doesn't support. Okay, that's better. Not better. We are getting an error, but at least we are getting the expected results, right? Right. So, what were we going to do? Oh, the code generation, right? So, if the operation is and then, or it is, or return if our key is equal to so our key should be castable to integer. The target key should also be castable to boolean, not integer. So I'm going to create a primitive type boolean type, which is type bool, like so, and I'm going to say okay. if I am compatible with boolean type, and if my target, which is this one, compatible with boolean type, return true. So they don't have to be boolean directly, but they have to be compatible. I can get rid of those. Okay. They don't have to be booleans directly, but they have to be compatible for sure. For example, they could be pointers that are then casted to boolean. Right. And what is our type? Well, if you know what, doing that, or OP is and then, or OP is or. Right. So that's the type gen, and for actually generating the operation, we have a lot to do. We have a lot to do. Okay, so if OP is and then, let's start with the and then we can implement or as well, right? The first thing that we want to do is cast in the LHS and RHS to Boolean types. So I am going to create another primitive type, name it Boolean type, like so. Replace LHS with a cast, So how does cast work? Is it type first or the other one? I think it's type first, but I could be wrong. Are you happy? You're not happy. Okay. This one. Expression and then type. Right. So this should work and it should be new. Do the same thing for RHS. And then LHS dot prepare just in case you need to, and LHS dot compile just in case you need to, and then RHS, do the same thing for RHS as well. So now we know we are dealing with integers. We know we are dealing with integers. We want to look at the first one. We want to look at the first one. So we are going to create an lookup. CC builder, CC LLC builder, create an lookup for me. So what's the lookup type? And what's the name? So the type would be LLVM primitive type. Sure. No. The type would be, I know what's Boolean type dot type gen. Thank you, ABS GASM, for following us. Welcome to our stream. Okay, so define. Let's look at define for a second. I need to pass 0 and then the name. Okay, so we are passing 0 after that, and the name would be and send that. Right. And I guess I can close that. This is LLVM type. Okay, so we have that, and we are capturing that into the out value, and we do some operation, and then we want to return that. In the end, we want to return that. Right. So we have to jump through 2 steps. So I'm going to first look at the LHS. So I'm going to create CC LLC builder, create conditional PR. So what's the condition? The condition is left hand side. Look at the left hand side value. Mm, and if it was true, jump to can't be, otherwise jump to false be. And I will define those as well. And then set the builder, set the insert point on the condition block, where we are going to look at the RHS. And this would go to either true B or false B. And then set it to false B, at which point we are going to say, oh, this is going to be create store. This is going to be ugly. Create a store true. I'm going to handle that. And then the value would be out. So a store false here, false value here, and then jump to create PR, not conditionally, jump without any condition to continue block. Finally, go to the true block, do the same thing, only instead of false V, it should be true V, and then continue block, and then set insert point to that. Set insert point to continue block and return a load. CC LLC builder create load out. Okay, so we need to have 1, 2, 3, 4 blocks. We start in another one, so we have 5 blocks in total. Let me try to visualize that. So we start in block 1, or in the in the function block, whatever that might be. We are doing something. For example, we're adding, we are multiplying, whatever, and then we decide to check the and operation. So we look at the left-hand side, and we either jump to true or to false. If we jump we either jump to check RHS. So if we jump to check RHS, we want to look at the RHS and jump to true or false. And if we jump to true, we basically set out equals true. Then jump to continue. If we jump to false, we set out equals false, and then jump to continue. And then in the continue block, we say, okay, the expression that you wanted is in out. Use it. Right? So this is what we want to do. Let's double check to see if it is happening. So we start somewhere. We cast them to Boolean values, but we don't execute them. That's the important part, right? We look at the left-hand side, jump either to condition or to false. In the condition block, we check the right-hand side and jump either to true or to false. In the false block, we set it to false and then jump to continue. In the true block, we set it to true and then jump to continue. So it is correct. It is in fact correct. Now, to create this blocks, I am going to cheat because I don't remember how to do that. LLVM basic block, whatever. Okay. So we need to have a lot of different blocks. Basic block. So the first block is condition block, which we get from LLVM basic block creates context, name, and the function. Okay. Context is cc llc context. Name is and condition, and the function is f. I have to get f from cc llc f. Right. So that's the condition block. The false block is there also, and false. The true block is there also. Let's call it and true. And then we have the continue block. Let's call it continue block and continue block. Yeah, that would be better. So that when we're looking at the generated code, we can quickly realize what's happening. As for the false value and the true value, well, let's look at the const int. Right, we want to do the same thing here, so I'm just going to copy that. Right, so we want to get an integer of size 1 with a value of false, so 0. And for the true, we want to get a value of 1. So I think this should be correct. Potentially, we might not need to do the load, but we'll see. So let's go to our test 5, and I am going to comment the majority of this out so that I can test it quickly. Okay. Compile. Let's see if it works. It does. Let's look at the code. So we are here. I think if condition, yeah. So we do whatever we want to do, and then we, based on the output of the left-hand side, jump to AND condition or AND false. In the AND condition, we do the other chest and jump to AND true or AND false. In the AND false, we store false inside of it. In the AND true, we'll store true inside of it, and then we load it and pass it to the whatever wanted the AND operation. So that seems to be correct. Let's see if it actually works, and it does. That's the AND. Let's do the same thing for for the OR. So quick test. I know that this works. What if I say not here? Okay, that's correct. What if I say not here? Oh, no. That shouldn't be happening. Damn it. Okay, let's look at what we did wrong. Let's look at the generated code. So this is as before. We are XORed with true so that we get the not, I believe. Does that make sense? Yes. And then if it was true, jump to true. If it was false, jump to false. Okay. It seems to be correct. I don't see what I'm doing wrong here. This is correct, right? I modulo 3 would be 0. It's not equal to 0, so this would be true, and it will be false. And we are doing here, we are calculating the remainder of whatever I is with 3. We check that it be not equal to 0. We XOR that with true to get the, you know, the not operator basically. So what's happening here then? We jump to false, then we store false. Come on. Yeah, so the incoming of here is and true and false. So that's okay. We don't jump from any of the conditions to the continue block directly. That is good news. I'm guessing the RHS. Oh, am I generating the correct thing here? Yeah, RHS. Okay. I thought for a second that could be the problem. Come on. Let's see. Everything is at the latest version. This is at the latest version. I'm going to double check. Oh, what? Wait, what? Did I call? Let's see what I did there. Oh, right. We shouldn't get correct. We should get wrong. We should get wrong, not correct. Sorry. We should get wrong here, and we aren't getting wrong. So yeah, I got excited for a second. Um, let's see here. So we start. We look at the LHS. We jump either to condition and to false. We know it is true. We know the left hand side is true. So we go to the condition block. Condition block is here. We look at the RHS. We know it is false. So we jump to the false block, which is here. We get int1ty, the boolean type. We assign it 0. What is the third parameter? The third parameter doesn't matter. We assign it 0, and we store it inside out. Then we jump to continue. In the continue, we load it. Oh my god, I don't know what I don't know what's happening here. So could it be that I'm making a mistake here? Would this work? Maybe not is not working correctly. No. So it's like it's not considering the second one at all. Let's have a more simplistic approach. So if true and true, so we know that this works. We've seen a more complex example of it, but I'm just going to double check. Okay, that works. So if true, we know that this also works. I'm going to change this so I don't get confused. You know that this should also work. It does. Now, this should also work, right? It does. Now, for the tricky one, for this one. So the first one is true, the second one isn't. Let's see what happens. It says correct. Let's look at the code from start to finish. So I'm going to delete that window for now. Right. So we create an alloca A, which is a boolean. We store true inside of it, we store false inside of it, we load it, we apply not to it. And that worked. Because not false would be true and it is inside if. We know that the answer is inside if the first answer that we get. Yeah. So that's correct. Then we jump to if continue. And the if inside if continue, you define a variable I, you store 3 inside of it. Then you store 15 inside of it down here. Then we create an and temporary value with an alloca of 1. We jump to 1 if it's true, so we go to AND condition. In the AND condition, we jump to AND false because it is false. There, we store false inside AND temp value. And then we jump to AND continue, inside of which we will load AND temp value to %2. And then we jump based on that. Okay, I don't know what I'm doing wrong. And it's been 3 hours, I think. Yes. And I am honestly losing my mind here, so I'm going to stop it right here. And we are going to continue again tomorrow at around the same time. So thank you all for joining me today. I really appreciate you guys being here. And I hope to see you guys again tomorrow. Have a great day, and bye-bye. Oh, wait. I've been told I should rate other channels, and I know how to do that. I learned that how to do that. So if I go to twitch.tv, I guess Jonathan Blow is live, so let's go there and do that. Right. See you all there. Bye bye.